We are going to continue with our discussion on material objectivity. This simply tells us that the energy, stored energy, is invariant with respect to rigid body motion, right? So you had some deformation and you superpose on it any rigid body motion, then the deformation gradient F changes to QF. But then from physics, the energy remains invariant. So therefore, we say that W of F is equal to W of QF. Okay, for all Q, we say in SO3, spatial orthogonal group, which simply means for all Q in the rotation. For all rotation, this has to hold. Okay, so this is a statement in terms of energy. Can we have a statement in terms of stress, for example? So let me try to draw that picture and see if we can get that statement directly in terms of stress. So here is the reference configuration and that is the deformed configuration. And you further do rigid motion, rigid body motion through some translation T and some rotation Q. So the deformed configuration is simply going to rotate and translate, of course. And here is your small f. Okay, so, and then you have got a point here, big X, which has moved to a point small x here. And let's say this is small x hat. And finally to the point small x. Okay, can you hear me?
Yes, sir, you are audible.
Okay, very good. Now, what can you say about the transformation of Cauchy stress? So suppose in this intermediate configuration, the Cauchy stress is at this point sigma hat, and over here it is sigma. Then do you think sigma and sigma hat will be related somehow? What do you think? So from physics, what do you think? Is there any relationship between sigma and sigma hat?
So the since it is a rigid body motion, so should they be same?
I mean, same meaning what? The sigma tensor itself would be same?
Yes, sir.
Okay. Anybody else?
Magnitude and the direction of the forces, they remain the same. External
Are you
forces.
asking me or you are answering?
I'm asking you, sir, like in the intermediate configuration and in the final configuration,
Yes.
are the external forces acting in the same magnitude and direction?
Well, forget about external forces. It's just that the configuration of the body, somehow we have we are applying the forces in such a way that the configuration of the body is simply the rigid rotation of the intermediate one. So you may have to change the external forces, But finally, the configuration that is attained is simply the rigid motion of the intermediate configuration.
Sir, will
Yes.
sigma be Q transpose sigma hat Q?
Why do you think so?
Sir, like when we rotate this axis, then we define the changed configuration as like if we rotate the axis, then stress doesn't change, but like the component will change, and then we do Q transpose that stress matrix into Q to get the new components. So
See, that was the case where the stress tensor was the same and you were changing the coordinate system.
yes, sir.
But here it is not the same. Let me illustrate. Well, first of all, what Vinayak and many of you are saying is kind of, I mean, it is partially correct, but not exactly. And so I will illustrate to you what I mean. So think of a cuboid, because this is something you have been familiar with in your undergraduate. So this is a cuboid at a point x hat, centered at x hat, but within the body. Okay? And its three faces are along E1, E2, and E3, the normals. And let us say on E1 face, when you cut this section, then on the E1 face, the traction that you see or the traction that is acting, suppose it is T1. Okay. Likewise, on E2 phase, the traction that is acting is T2. And on E3 phase, the traction that is acting is T3. I hope this picture is clear to you. So traction acts on faces, isn't it? On planes, you have traction acting. And when you multiply with the area, you get the force on those planes. Or you have to integrate over the area to get the total force. Isn't it? Now these tractions have generated due to deformation of the body, due to shear strain or volumetric strain in the body. Now as you rigidly rotate the body, this cuboid is also going to rotate, right? Are you with me?
Yes, sir.
Yes, sir.
Okay. So this cuboid is also going to rotate, and now its face normal would have also rotated. Sorry. So, for example, this face, which was E1 initially, well, let's make all the intermediate ones as hat. So I'll make the intermediate ones as hat. This is E1 hat, E2 hat, E3 hat, and likewise the tractions are T1 hat, T2 hat, and T3 hat. And in the final, they are all without hats. So the normals, so this is going to be, sorry, the normals are with red color. So will this be same as E1? Sorry, will this be E1 hat, the normal? What do you think? Will it be same as earlier? It's the same cuboid. It is the same cuboid that we are looking at. Will the face normals remain unchanged or will it change?
So it will change.
It will change, right? So let us say it becomes E1, E2, and E3. And it will change in the following way, isn't it? EI equal to big Q into EI hat. Will you agree with this? Because all the vectors will simply rotate. And same thing goes even for the tractions. The tractions, won't the tractions also rotate? See, the magnitude is the same. It's just that the direction will simply rotate. So here it will be T1, then over here it's going to be T2, and here it's T3. Sorry, I have to put it as a superscript. And will you agree that TIs will also be Q into TI hat? Will you agree with this?
Yes, sir.
Okay, very good. Now, from the definition of stress tensor, let us think of sigma hat, for example. So we know that sigma hat, when you multiply with the surface normal, that's the Cauchy theorem. Let us say EI hat, then you get the traction on the EI hat plane. Is that correct? So sigma matrix, when you multiply with the normal, you get the traction on the normal plane, on that plane.
Sir,
But also, let's have a look at it from the linear transformation perspective. This sigma as a linear transformation. So we are already knowing how this sigma acts on three independent vectors, E1, E2, E3. And it is returning us T1, T2, T3. So, and also notice that E1, E2, E3 are perpendicular here. Then what can you say about this linear transformation sigma hat itself? What do you think? Remember your, I think, second lecture, perhaps second or third lecture. For a linear transformation, if you know how it operates on three independent vectors, then you know completely the linear transformation. And what is the formula for that linear transformation?
Hello?
Yes,
Hello,
hi
sir.
Niranjana. Yeah, yeah.
Sir, so it, TI had cross EI, sorry, not cross, tensor product EI summation.
True. So as Niranjana said, this is TI hat tensor product EI hat. See, both are hats, and you don't have to write summation because it is automatically implied, right? There are two I's. Similarly, think of the sigma linear transformation sigma, and we know that sigma into EI is equal to TI, right? Due to the property of the stress tensor, sigma into EI is equal to TI for the from the final configuration. So this tells me that sigma is simply Ti tensor product Ei. right? Now let us try to relate sigma with sigma hat. So that means sigma is equal to, see, it is Ti, which is Q into Ti hat. Tensor product EI, which is Q into EI hat, right? Now from the property of the tensor product, you could also write this as Q into Ti hat tensor product EI hat into Q transpose. So you have to just remember the identity that you learned maybe in third or fourth lecture. But now you see the thing inside the bracket is nothing but sigma hat. So this is how you relate sigma with sigma hat. So basically the stress tensor has changed here. Because the body has rotated, you see the body has rotated, therefore the tractions also rotated and the surface normals have also rotated. So therefore their tensor product will also rotate. So the stress tensor, when you rotate a body, does change. Just like every vector engraved in the body changes, the stress tensor also changes. So stress tensor is no more the same here. And the transformation is related through this formula. Okay? And this is also the statement of material objectivity. You can use either the energy one or this directly stress. And this is more general. This is more general statement of objectivity. Can someone think of why? That's because you cannot always write down the stored energy for all bodies. But stress you can always write down. But let us see for the bodies for which we can write energy, can we derive this property from W? So for bodies, or let us say for hyperelastic bodies, for which we have seen from physics that this is equal to W of F. Can this be used to derive this property? Can we derive? See, you can start with one and derive the other. So let us see, can we do it? So the first one is in terms of energy, and what we have to derive is in terms of stress. So can you think of what should be the way ahead? How do we derive it?
Sir, uh,
Yes,
why are we calling that above formula a more general statement of objectivity?
yeah, that's a very good question. And as I told you, it's because, for several bodies, you may not be able to write down the expression of energy. For an elastic body, for example, you can write W and then get stress from it. But let us say if you have a viscoelastic body in which there is also some dissipation, then there is also some energy being dissipated. So you cannot write down the full expression, the expression for the entire energy. It's difficult to write potential for the dissipated energy.
Okay, sir. But the thing that we just derived, that is always, uh,
Yes,
that
because you
will
see, this is
always remain.
directly from the sigma relation is directly from, I should say, from the configuration, and sigma is always there, no? Whether it is elastic body or viscoelastic, from the property of traction, you cut a section, you find traction, so it is always there.
Yes, sir.
So in this entire thing, we never had to bother whether the body is elastic or viscoelastic or plastic, right? Whereas for the W thing energy, we had to assume basically that it is a hyperelastic body, right? Then only we could think of W and whose derivative then gives us a stress. Okay, so what do you think now? How can we derive from W and going to sigma? Anybody?
Hello, sir.
Yes.
Sir, can we begin with because we have defined earlier in the class the Piola-Kirchhoff stress equal to dW by dF.
Yes. So what you're saying is to take the derivative?
Yes, a partial derivative with respect to f.
Right. So I think that's a way ahead. So we have to take the derivative of this relationship. Now taking the derivative is not so easy. So we can scalarize this. I mean, we can scalarize the differentiation. And let me show you how to do that. So suppose that f is changing to f plus alpha times a. And then you think of taking the differentiation with respect to alpha. Okay, so this is very much, so see, in this way we are changing all the components of f. So Fij is being changed to Fij plus alpha Aij. So all the components are simultaneously being changed, and this allows us to take the differentiation in the usual way. So basically we can first write down the relation. So it is going to be the W of Q times F plus alpha A, that is equal to W of F plus alpha A right? Now let us do its d by d alpha, the whole thing at alpha equal to 0. So what are you going to get then? Any idea what will you get? So maybe think of using chain rule and call this thing as big Z. So we can say it is del W over del Z ij into del Z ij. Well, it now becomes dzij over d alpha. Is that okay? I have used chain rule. Okay, and this entire expression has to be evaluated at alpha equal to 0. And likewise, it goes for the right hand side. So this is equal to, let us say this is maybe V. So we have del W over del Vij into dVij over d alpha. And this thing also has to be evaluated at alpha equal to 0. Okay, is that okay with everyone?
Yes, sir.
Okay. Now, what is this thing del W by del Z? What is this thing? So when you take the derivative of W, what do you get?
Sir, with respect to f we take, then we get p.
But you see here, it's not like you have to take respect to f. You simply have to take derivative with respect to the argument, and then you get p. So both del W by del Z on the left hand side and del W by del V on the right hand side, both give you P. So I can write it as, this is quite, I think this is a bit confusing. When I did it for the first time, it was confusing for me also. Should I call it P or should I call it something else? But I'll repeat that again. Let me write it down. So this is Pij, but evaluated at Q of F plus alpha A. So evaluated at Z basically, which is Z, into dzij by d alpha. What will be dzij by d alpha?
K, sir.
Ij.
We can do a side calculation here. So Z is equal to Q times F plus alpha A. So that means Zij will be equal to Qik into F kj plus alpha A kj. Isn't it? Let me make it clearer. So this is Qik into F kj plus alpha A kj. Okay, so what is then dzij by d alpha? So that's simply qik into a kj. Okay, we can now put it here, and this becomes qik into akj. You see, we have to go very slow, and we have so much of time. Okay, so that's a nice thing when you are doing higher level course or research. You have a lot of time. You don't have to worry about time, but you have to have patience. Go slowly. So, and this entire thing has to be evaluated at alpha equal to 0.
Sir, this p is the same p as Piola-Kirchhoff?
It's the same P as Piola-Kirchhoff, yes.
But sir, then we did that it will be del W by del F. So why in this case we are...
Right. I'll tell you. Okay, don't worry. Let me just complete this. So on the right hand side also it is Pij, but evaluated at V, which is F plus alpha A, and multiplied with dVij by d alpha, which will simply be Aij. Okay, now coming back to this very interesting question, why are they P? So the answer to this is, I'll do a side calculation here. See, so we have W as a function of QF, right? So QF is just like some another F. Let's just say F star. And what will be P? P is simply del W by del F evaluated at F star. So P at F star is del W by del F at F star. So you see, in fact, inside the argument, it could be simply WZ. You could just write WZ. Or you could say it is WF is equal to Z. And then you want to take the derivative. Is that making clear to you? Maybe perhaps not. Let me see it again. So what we have is W of QF. Now the question is, if QF I say is Z, is del W by del Z also P? Then the answer is yes, because P by definition is simply the derivative of W with respect to the argument of W. And inside the argument, you could put QF or QF square, whatever you want to put. P is simply the derivative of W with respect to its argument. That's it. So I think the confusion arises because we always think that P is del W by del F. But in fact, P is just the derivative of W with respect to its argument. That is it. Is that, does it make clear? QF
So,
is like another F, and you are
so
just taking derivative to W and evaluating at that particular F. Also it's like, think of a function f of x is equal to x square. Then what is f prime? It's 2x, right?
Yes, sir.
Now suppose I say f of x equal to 2y. So it is 4y square. Then what is f prime? So what is the meaning of f prime first of all? F prime just means whatever is the argument, you are taking the derivative with respect to argument. That is it. So if it is argument is 2y, you have to somehow take derivative with respect to 2y, not with respect to y. So that's the meaning of when you say f prime. So this means derivative of f with respect to its argument. And inside argument, it can be anything. So you could also say this is equal to z, and then this is x square, or you also say it is z square, x square, or z square.
Sir, what
Okay,
happens if
so just a second.
W? Yes,
Let me evaluate f prime now. So f prime, as I said, is the derivative of f with respect to its argument. So the argument, if I think as x, then it is what? So it is del f by del x, sorry, df by dx, sorry, it's just one of them, no? So df by dx, but f is x squared, so it is 2x, right? And then you plug in x equal to 2y. If you want the result in terms of y, plug in x equal to 2y and you get
4y.
4y. Do it another way. If you think of it as a function of z, then it is df by dz, which is again equal to 2z, and you plug in then z equal to 2y, which, and again you get 4y.
Yes, sir.
If you want to take derivative with respect to 2y, think of 2y as w, okay? And then you have df. So if you think of 2y as w, then again on the right hand side you have w square. So df by dw is then 2w, and you again plug in w equal to 2y, you get 4y. So in all the cases you are getting 4y, but the meaning of f prime is derivative of f with respect to its argument. And you should not make a mistake here. If I say f of 2y, I wrote here, and I say 4y square, and then you say that, oh, okay, so then df by dy is equal to 8y. I mean, you then say that f prime is then equal to 8y. You can't say this. So this is going to give you a wrong result. Because you see, in each of the cases, you are getting 4y, not 8y. It's the same thing here also. So P is simply W prime. It's just that here prime means scalar derivative, whereas above prime means tensor derivative. So P is just W prime with respect to its argument. Therefore, del W by del Z, so this thing here and this thing here, both are P, but obviously at different arguments. The after getting P, you have to evaluate it at different arguments. Here it is Z, and here it is this F plus alpha A. Is that clear to you now?
Yes, sir.
Yeah, I mean, you can think about it a bit more. But it's simply that P is the derivative of W with respect to the argument. So let us now proceed further. And when you evaluate at alpha equal to 0, you are getting Pij at QF, right, is equal to, sorry, into Qik Akj, and that's equal to Pij at F into Aij. Okay, so what can we make out from here? See, finally, we have to take A outside. We have to somehow get rid of A so that the remaining thing we can equate on both the sides. So is there a way to do it? So this can be written as Q transpose Ki into Pij at Qf into Akj. That's equal to Pij at F into Aij. Okay, now you see what is this thing here? Q transpose Ki into Pij. Isn't that simple matrix multiplication? Multiplication of Q transpose and P, and then you take the Kj component. So in the tensor form, I could write it as Q transpose into P and take the Kj component. Multiply with Akj, and that's equal to Pij into Aij. Okay, which is again, and can you see what is this? This is also double contraction, isn't it? And P has to be evaluated at QF. Remember this. Double contracted with A, that's equal to P at F double contracted with A. Okay, so now you see we have been able to take A separate on both the sides, and since it holds for any arbitrary A, this implies Q transpose P at QF is equal to P at F, or the final statement that P of QF is equal to Q into P of F. Okay, so this is the statement of objectivity in terms of Piola-Kirchhoff. So we got it from W of QF equal to W of F. Okay, finally for the sigma. So sigma, do you recall the relationship between sigma and P? So sigma is 1 by det F into P into F transpose, right? So this is when F is F, but when F becomes QF, then sigma at QF is then 1 by det QF. See, F is QF. Wherever you have F, replace it with QF into P at QF into QF whole transpose. Okay, sorry, I was going in a curve fashion. So this is also equal to 1 over determinant of F, right? Because determinant of QF is same as determinant of Q into determinant of F, but determinant of Q will be equal to 1 because Q is rotation into P of QF into F transpose into Q transpose. Okay, and yeah, now plug in the formula for PQF from here. So this is same as 1 over det F And PQF, we just saw it is Q into P at F into F transpose into Q transpose. Okay, but then you see this thing here. What is this thing inside the green box? Isn't this same as what it is here? So this finally means that sigma of QF is equal to Q into sigma of F into Q transpose. Isn't this what we wanted to prove? You see, the final thing. Okay, is that so? You see, this is how we can derive this relationship starting from W. Is it clear to everyone? Roshan?
Yes, sir. Sir, here F is the intermediate and QF is the final.
Yes, yes, correct. F is the intermediate, QF is the final. Isn't that what it should be? Because you
Yes, sir.
see from the original picture also,
Yes, sir.
sorry, you can, yeah, even from the original picture, Q is done afterwards, so the final one is Q into F.
Yes, sir. Sir, also, how are we eliminating the A that the term A that we had?
Yeah, that's as you can see, we just did index thing all along. So we had this A here,
Yes, sir.
we wrote it in the index notation, kept going, and finally our goal was to separate A.
Yes, sir.
So we had to think of how can we arrange the terms so that we can separate A. And then we came here,
Yes, sir.
and you can see that A is separate.
Yes, sir.
Since it holds for arbitrary A,
So we are
so the
canceling
thing
it.
without A should be same.
Okay, sir.
Yeah. You should try such a thing with other examples so that you can become master also. Okay, so we derived this property of MO in terms of stress. Finally, you can recall in the last class we said that any good constitutive relation automatically satisfies angular momentum balance. So let us try to derive that property also. So we are now ready to derive that. So what should we do? Um, yeah, so for this, see, I know how to prove it. So therefore, I know what to start with. Otherwise, it is not so easy to think of what I should start with in order to prove that any good constitutive relation automatically satisfies A and B. And I also think someone who did it for the first time must have been thinking a lot, okay, how can we prove? And he must have just stumbled upon this proof. So anyway, so again, objectivity means W of QF is equal to F, isn't it? Now I'm going to think of a special Q, but now the Q is a function of time. Okay. Now since Q is rotation, so this implies Q into Q transpose is identity, right? Is that known to you? That the transpose of Q will be same as the inverse. which means that QQ transpose is identity. Are you all okay with this?
Yes, sir.
Devjit?
Yes, sir. Yes, sir.
Okay. Now, see, it is a function of time, but Q. But the right-hand side is not a function of time. So why don't I take the derivative? So I'll get Q dot into Q transpose plus Q into Q dot transpose equal to 0, which means Q dot into Q transpose is equal to minus of Q into Q dot transpose, which is same as minus of Q dot Q transpose transpose. Can you write it? You can see the final thing, take the transpose, the order flips, and you get what it is here. So what you see is that Q dot Q transpose, if it's a matrix, then it is equal to negative of its transpose. So Q dot Q transpose must be skew symmetric. So it must be skew symmetric. Okay, so let us define Q dot Q transpose is equal to some omega, skew symmetric. Okay, and if you further think of little omega is equal to axial of big omega, then this turns out to be the angular velocity corresponding to Q. So if Qt is known to you, this angular velocity is simply axial of omega, which is also axial of Q dot Q transpose. Okay. Now suppose that this omega is constant. So this is then a constant, which also implies Q dot is equal to omega into Q. Okay, but with omega constant. Now, do you guys know about this thing that x dot equal to ax? What is its proof? What is its solution? Is it so? X equal to e to the power ax? Must have seen this, no? Sorry, x equal to e to the power at. Have you seen this? Anybody who has not seen it? Niranjana, have you seen it?
So here are you speaking about component wise of A?
Well, here it's all scalar. X is scalar, A is scalar.
Oh, okay.
And then, yeah, you must have seen it, no? Anyone
Yes.
not seen it? ये तो बहुत आसान है, इसको क्या लिखेंगे? dx by dt is equal to a into x. Now you do the separation of variables, so dx by x is equal to a dt. Then integrate, so you get ln of x is equal to at plus some constant c. Then you take the exponential on both the sides, so you get x equal to e to the power at plus c, which is equal to some x naught into e to the power at, where x naught is equal to e to the power c. So basically, so here I have missed something. You'll have some x naught. So this is with scalar. Similar result holds with matrices also, and you can say that q of t will be equal to e to the power. Well, this is equal to some q naught into e to the power omega of t, but only for omega constant, just like here E is constant. Okay, is that okay with everyone?
Yes, sir.
So for a constant omega, this simply means I'm thinking of a rotation which is rotating about a constant, rotating at constant angular velocity, because omega is constant, so small omega is also constant, so angular velocity is constant. It's not changing with time.
Sir, can we have matrix as the power of exponential?
Yes, yes, of course have. And it's there are several complications also involved while taking the exponential of a matrix, but I'm going to skip that. But yes, you can do the exponential of a matrix.
Okay, sir.
Yes. Okay, so let us think of this particular Q in our objectivity formula over here. So it simply means you have a body and you are rotating, you have deformed it, and then you are rotating the deformed body at constant angular speed. So at every instant of time, W will be same as what it was equal to 0. Right? Because it's the rigid rotation all through the time, so it's not going to change your W. So that's what we are thinking physically here. So W of Qt of F is equal to W of F. All right. Now let us do the d by dt of this thing. And see what we get. So we have to again do the same way as it earlier, I guess. So in fact, Q is already a function of time here. So we already have a parameterization involved here. So we don't really have to go back to what we did. So think of this as Z. Okay. And so you are going to have del W over del Z ij into dzij by dt, isn't it? And isn't the right hand side equal to 0? Because right hand side there is no function of time. Are you guys with me?
Yes, sir.
Yeah, yes, sir.
Okay. So now del W by del Z is simply P, as we have seen. It is Pij, but evaluated at Zij. And dzij by dt is then going to be Q dot ik into fkj. Is that okay to you? Because this is q into f, no? And you have to take the derivative with respect to time. Anybody having problem here? So if you have any problem, please ask me. Okay, so what can we do now? So I'm going to sneak in a Q. Can we say it is same as P at QF double contracted with Q dot into F. Would you agree with this? And that's very simple. This is directly coming from here. You guys are not saying anything. I hope you are following it. Rajneesh?
Yes, sir. Yes, sir.
What about Nomendra, Adil?
So can it be that the deformation gradient is also a function of time?
It can be, but for this particular case, we are not thinking of that.
Okay.
Because we want to apply objectivity, no? If you also make deformation gradient function of time, the energy will start changing.
Yes, sir. Okay, okay.
Okay, so yeah, so I'm going to write it as P of QF double contracted Q dot Q transpose into Q into F. Okay, that's equal to 0. So then I'll say this is P of QF double contracted. See, it is all mathematics going on, but final result will be, as I told you, surprising. So Q dot Q transpose is now big omega, which is a constant, into Q at T into F equal to 0. Okay. Now let us evaluate this at T equal to 0. So at T equal to 0, Q will be equal to Q naught, right? Using this formula. Put T equal to 0, it is e to the power 0, which is identity. So Q0 is equal to Q naught. And suppose that we are having such a rotation that Q naught is equal to identity. Okay, so we are starting with a rotation such that at T equal to 0, it is identity, and then it is building up on it. So there is no rotation at T equal to 0, therefore it is identity, and then body is orienting, changing the orientation. That's what it happens physically, you know. So at T equal to 0, then Q becomes identity. So it is P of F double contracted with omega F equal to 0. Okay. Now, have you guys, did you learn that A double contraction B is same as trace of AB transpose? Had I taught you earlier? I mean, you can also see this. What is A double contraction B? It is Aij, Bij. But here, trace of AB transpose is what? So Aij into B I, so B, first of all, the multiplication will be Aij into B transpose Jk, which is same as Bkj. And then you have to make K equal to I to get the trace. So this is then finally Aij into Bij, since you want the trace. Okay.
Yes.
Okay, so
Yes.
let's come back here. So this double contraction thing means it is trace of P into omega F transpose, which is same as trace of P F transpose into omega transpose. equal to 0, right? Which is same as PF transpose double contracted with omega equal to 0. Can you see this? Because now you think of this as another matrix or tensor, and this is another tensor. So it is A into B transpose. Trace of A into B transpose is same as A double contraction B. Okay, and this thing, all of you must have come across this in your angular momentum balance assignment. Did you come across this?
Yes, sir.
What does this tell you if omega is arbitrary? See,
PF
omega,
transpose
PF transpose should be 0.
0.
not PF transpose should be 0. The symmetric PF transpose should be symmetric. That's the
Symmetric, yeah.
its anti-symmetric thing should be 0. I think you must have seen this in your assignment, not the proof.
Yes,
So
yes,
this
sir.
holds for r bit omega. And so from the assignment, this tells us that PF transpose must be symmetric. Using assignment proof.
Sir, most of them are using Cauchy, but here we are somehow changing to the reference frame and then shifting to Piola-Kirchhoff and this. Sir, why is it? Why is it that we are always shifting to Lagrangian and they are continuing with the Eulerian reference as it
Who
is?
is continuing with Eulerian? I mean, everybody. If if you want fully Lagrangian framework, then you have to do everything in terms of Lagrangian formulation.
Yes, sir. But in the one two books that I came across, they have what they have done is they have proved that the Cauchy stress tensor is symmetric, and thus they have derived the expression for proved the derivation for angular momentum. So
Yeah, I mean, the proof of Cauchy symmetric being symmetric, Cauchy stress tensor being symmetric is a Eulerian proof, no?
yes,
You
sir.
work
That is what I was
Eulerian,
saying.
but we wanted to do it in a fully Lagrangian framework.
Yes, sir.
So this is how you will do it. If that book didn't do it, then it's simply that they didn't do the Lagrangian framework. Anyway, so the theorem that we want to prove that you A tensor product B is equal to 0 for all is QB, then A must be symmetric. This is what we have to prove. So let us see how we can prove it. So select A as a symmetric part. So I say gen ij bij plus A anti-symmetric ij bij, right? This is A product B. Is that okay with everyone? Now, because this is asymmetric, so I could also write asymmetric Ji, isn't it? And J, because B is Q, it becomes of Bji. Is that correct? Then we go to second term. So this is equal to this plus AA ij bij. and this is said to be equal to 0. So this is equal to 0 and this is also equal to 0. So both are. Now can I add these two? Let me add these two. Let us say this is 1 and this is 2. And you notice that the first term here, j and I are dummy indices. So you could flip it, make ji and ij. And then you see that this and this, they are same thing, isn't it? Because I and j are dummy indices and you can flip them. But when you add 1 and 2, they will then cancel because of the presence of a negative sign here. So you have a negative sign. So this implies Aij into Bij is equal to 0. Now, okay, so antisymmetric part, so why don't I write it component wise? So this also means, well, let me write it in the matrix form. So Aij will have A, B, sorry, on the diagonal it is 0. So it is A, B, C, 0, 0, 0, minus A, minus B, minus C, right? This is the general form of antisymmetric matrix. And I have to double contract this with B, which is also 0, 0, 0. And let us say this is, okay, maybe I should have made A1, A2, A3 for A. A1, A2, A3 minus A1 minus A2 minus A3. And here you have B1, B2, B3 minus B1 minus B2 minus B3. And when you double contract, so this has to be equal to 0. When you double contract, you see what you're getting. So it is 2 times A1 B1 plus A2 B2 plus A3 B3 equal to 0, isn't it? And this has to hold for every B, for all B1, B2, B3. So if you take B2 equal to 0 and B3 equal to 0 and B1 not equal to 0, this becomes, so if you take B2 equal to B3 equal to 0, you get A1, B1 equal to 0, which implies A1 is equal to 0, right? If you take B1, B2 equal to 0, this becomes A3, B3 equal to 0, which implies A3 is equal to 0. So likewise, you can take another case and show that A2 is also equal to 0. So this proves that all three components of the antisymmetric part is 0, right? Which implies that A will not have antisymmetric part, so A must be symmetric. So that's the proof. Is that okay? So finally, this means A is symmetric, which also means that PF transpose is symmetric. So you see, what we have proved is that if you have a good constitutive relation which satisfies objectivity, then angular momentum balance is automatically satisfied, and therefore while solving the equations of equilibrium, you can forget about the angular momentum balance equation and just work with the linear momentum balance and solve for the unknown little x. Okay? So, see, isn't it magical that a good constitutive relation automatically the the implies that the A and B is satisfied. It's really magical. और इसका तुमने ये देखा है, ये लीनियर इलास्टिसिटी में क्या करते हैं? लीनियर इलास्टिसिटी में भी एक लीनियर मोमेंटम बैलेंस का इक्वेशन होता है और एंगुलर मोमेंटम का होता है कि सिग्मा इक्वल टू सिग्मा ट्रांसपोज। और वहां भी हम लोग सिग्मा का ऐसा रिलेशन लेते हैं कि वो सिमेट्रिक होता है। तो वहां भी स्ट्रेस स्ट्रेस रिलेशनशिप ऐसा लेते ही है कि वो सिमेट्रिक होता है। तो इसलिए एंगुलर मोमेंटम बैलेंस वाला इक्वेशन को कभी हमें सॉल्व नहीं करना पड़ता है। और ये जो है, दिस इज द एक्सटेंशन ऑफ दैट सिग्मा इक्वल टू सिग्मा ट्रांसपोज टू finite elasticity. And this actually is not just for elasticity, this is for any general deformation. Even plasticity भी रहता है तो भी ये रहता है कि PF ट्रांसपोज जो है सिमेट्रिक होगा।
सर ये AMB का एक अलग प्रूफ भी है, मतलब इससे हम लोग AMB प्रूफ ये एक तरीका है एंड अदर एक गॉस डाइवर्जेंस से हम लोग जो करते हैं, ये दोनों वे से कर सकते हैं।
हाँ, जो
Like,
नहीं,
yes,
ये
sir.
भी का प्रूफ नहीं। दिस इज नॉट ए प्रूफ ऑफ AMB, दिस इज जस्ट हाँ बोलो।
सर रिजल्ट तो सर लास्टली हम यही ला रहे हैं कि PF ट्रांसपोज इज
रिजल्ट
सिमेट्रिक।
ये ला रहे हैं, बट हमें ये थोड़ी पता था कि ये AMB होता है।
अच्छा
रिजल्ट बस ये आ रहा है कि PF ट्रांसपोज सिमेट्रिक होगा, बट ये तो नहीं पता है कि यही AMB है।
यस सर।
हम लोग स्टार्ट किए ऑब्जेक्टिविटी से और प्रूफ कर दिए कि PF ट्रांसपोज हमेशा सिमेट्रिक होगा, बट ये AMB है वो पता नहीं है। उसके लिए हमें वो करना पड़ेगा, वो गॉस डाइवर्जेंस थ्योरम वाला जो कर रहे थे।
ओके सर।
सर यहाँ पे हमने अज्यूम किया कि f टाइम का फंक्शन नहीं है और एनर्जी भी चेंज नहीं हो रही है टाइम के साथ। तो सर ऐसा कोई एग्जांपल है क्या जहाँ पे f और एनर्जी दोनों टाइम के साथ चेंज होगी, टाइम का फंक्शन होगा f?
बिल्कुल एग्जांपल है। तुम जस्ट थिंक ऑफ ए बीम, ठीक है? उस बीम को क्या करो, या स्प्रिंग ही ले लो। आई मीन बीम इज ऑल्सो लाइक एन स्प्रिंग। एक फ्लेक्सिबल रबर का बीम ले लो, उसको जो है स्ट्रेच कर दो और फिर छोड़ दो, तो देखोगे कि वो जो है ना वाइब्रेट करेगा और धीरे धीरे डैम्प आउट हो जाएगा। तो उस केस में टाइम के साथ जो है डिफॉर्मेशन ग्रेडियंट चेंज हो रहा है वहां पर।
सर सारे हिस्टेरिसिस जो मटेरियल शो करते हैं वो ये शो मतलब वो सब टाइम डिपेंडेंट होंगे?
नहीं, नॉट जस्ट हिस्टेरिसिस, इवन प्योरली इलास्टिक केस वाला भी ऐसा हो सकता है।
ओके सर।
जैसे प्योरली इलास्टिक में अगर वही एक बीम ले जो कि इलास्टिक बीम, परफेक्टली इलास्टिक, जो कि रियलिटी में कभी होता नहीं है, बट मान लो परफेक्टली इलास्टिक बीम है, उसको फिर से स्ट्रेच करके छोड़ेंगे तो हमेशा ऑसिलेट करते रहेगा, वो कभी डिके नहीं करेगा, उसी एम्पलीट्यूड से ऑसिलेट करता रहेगा। तो उस केस में भी एफ जो है टाइम के साथ चेंज हो रहा है, बट इट्स ऑल्सो प्योरली इलास्टिक केस।
ओके सर। सर कोई भी मटेरियल प्योरली इलास्टिक नहीं होता है, लेकिन जब हम डिजाइनिंग की बात करते हैं तब हम मतलब जो प्योरली इलास्टिक के लिए जो लॉज वगैरह होते हैं उन्हीं को लेके हम लोग यूज करते हैं। तो सर ऐसा क्यों फिर?
Yeah, that's the limitation of our design, because purely elastic case is easier, and also this is where engineering lies. Maybe the material is not purely elastic, but it could be almost elastic. So in engineering we always learn how to approximate things to simplify the analysis. So it may be that the material was really almost elastic, so one can forget about the inelastic behavior there.
Okay,
But
sir.
if the material is really showing inelastic behavior, then you can't neglect it when designing it.
सर जो इलास्टिक मटेरियल है नहीं है वो सर एक्सपेरिमेंट से ही पता करते हैं, मतलब अगर वो हुक्स लॉ सेटिस्फाई कर रहा है, उसका कर्व पूरा लीनियर आ रहा है, तो फिर उसको मतलब परफेक्टली इलास्टिक मान के उसको सॉल्व कर सकते हैं, ऑलमोस्ट लीनियर आता है तो।
नहीं, लीनियर इलास्टिक का मतलब ये नहीं कि लीनियर इलास्टिक में जो है नॉन लीनियर भी होता है।
यस सर, मतलब वापस फोर्स हटाने के बाद में वो अपनी ओरिजिनल पोजीशन पे आ
It
जाए।
follows the same curve. So the stress strain curve, as you load it, it will exhibit some curve. So let me draw that here. So if it is sigma versus epsilon, so as you load it, initially it will be linear, then it becomes non-linear, and if you unload and it follows the same curve, then it is elastic. But if you unload and it goes like this, then this is inelastic. And then this is the dissipation, right? You must have seen this. Okay.
ओके सर।
Sir, here we assume our material is hyperelastic. Yes, sir.
Where?
Here, sir, all we have derived right now, sir.
Right now that we have derived, and wherever we assume W, that means it's hyperelastic.
Yes, sir. That
If
means
we
non-linear relationship, but stress strain follow also.
say again, non-linear?
सर यहाँ हाइपर इलास्टिक तो वही होते हैं ना सर, जो कि नॉन लीनियर भी फॉलो करते हैं बट लेकिन स्ट्रेस स्ट्रेन लॉ को फॉलो करते हैं।
देखो, हाइपरलास्टिक का मतलब ये नहीं कि सिर्फ नॉन लीनियर ही हो, लीनियर भी हो सकता है।
नहीं, यस सर, लीनियर भी हो सकते हैं बट नॉन लीनियर भी कंसिडर कर सकते हैं हम लोग इसमें।
नॉन लीनियर भी कर सकते हैं उसमें। सो W कैन बी एनी जनरल फंक्शन जिसके कारण जो स्ट्रेस स्ट्रेन रिलेशनशिप आता है वो भी जनरल होता है, नॉन लीनियर भी हो सकता है। बट जब उसको अनलोड करेंगे तो उसको सेम पाथ पे जाना है क्योंकि इलास्टिक है।
यस सर, यस सर।
यस।
सर प्योरली इलास्टिक होने के कुछ डिसएडवांटेजेस भी होंगे ना मटेरियल के, जैसे आप बात कर रहे थे कि अगर कोई।
वो वाइब्रेशन को एब्जॉर्ब ही नहीं करता है खुद से,
हाँ सर, हाँ सर, एग्जैक्टली।
वाइब्रेट करता है। दैट्स द डिसएडवांटेज।
सर एक लास्ट लेक्चर में आपने एक बात बोली थी, इन आइलेरियन फॉर्म LMB एंड मास कंटिन्यूटी कैन नॉट बी डीकपल्ड। सर वो ज्यादा समझ में नहीं आया, मतलब हमको दोनों यूज करना पड़ेगा ऐसा कुछ?
Okay, so in Eulerian form, LMB is divergence plus body force is equal to density acceleration. And whereas the continuity equation is, I forgot that formula, is it del sigma by del T plus divergence of rho V, is that equal to 0? So you have to take it, okay? I may be incorrect. Check.
Yes sir, it's correct.
So you can see that if you just think of solving LMB, so here you can plug in sigma in terms of F through constitutive relation, and A is also in terms of F. So everything is in terms of F, but you also have rho here, right? So you have two unknowns here, F as well as rho. So total of 4 unknowns, but only 3 equations. So you cannot solve it just using LMB. You also have to have this continuity together. तभी तो 4 equation 4 unknown होगा. Whereas in Lagrangian form, you have divergence of Piola-Kirchhoff
सर वहाँ पे
एंड दिस
रो
इज
नॉट
वेरिएंट और ये है लैग्रांजियन प्लस रो नॉट इंटू बी इज इक्वल टू रो नॉट इंटू ए। तो इसमें देखो रो अननोन ही नहीं है, रो नॉट तो नोन होता है ना। ये
यस सर।
3 अननोन है और 3 इक्वेशन है, तो इसलिए यहाँ पे हम लोग सॉल्व कर लेते हैं विदाउट कंटिन्यूटी।
जी सर, आ गया समझ सर, थैंक यू।
ओके, वेरी गुड।
Sir, today we learned that uh, anything like dw by dz. So, anything in the argument of w, uh, we will take as a Piola-Kirchhoff stress.
Yes, yes.
So, my question is, z can be any physical quantity, or it is just a function of
It's
f
just a
and x?
mathematical variable. Z is just a mathematical variable denoting the argument of W.
Yes, sir. But today means like we defined in the local what is it called, in the local density function something the Cauchy stress as a function of f and capital X, and and from there we again from there we are driving this relationship.
Can you please say where exactly you are saying? I am not able to.
Sir, when in the last lecture
Yes.
we were defining local elasticity theory.
Yes, yes, yes.
There we defined Cauchy stress as a function of f and capital X.
Okay.
And there this P Piola-Kirchhoff equation, the stress
Yes.
was a function of f and capital X.
Yes.
So now when we are defining dw by dz as a Piola-Kirchhoff equation, so how then z can be any physical
Yes.
quantity except f and capital X?
Simply, what I meant is, see, I said Z to denote the argument, but W will be some function of f. It could be f square. इसके अंदर में f स्क्वायर हो सकता है या f स्क्वायर q स्क्वायर हो सकता है, कुछ भी हो सकता है। तो दैट इज द आर्गुमेंट ऑफ z, दैट इज आर्गुमेंट z।
So yeah, yes sir. That's what
दिस इज व्हाट
I was confused that. Yeah. And
या
sir,
यहाँ पे
what kind of energy?
हाँ, say
What
again.
kind of energy? What kind of energy W is? Because we have also some in one step we proved that W is independent of translation and rotation. So in this
Yes,
way, W cannot have kinetic and potential energy. Also, kinetic and rotational energy. Also, we define this W as a strain-free energy. So, what kind of
yes,
exactly this W will be?
yeah. So
W
this is stored energy within the body. So it of course does not contain kinetic energy or that potential energy due to gravity, but it has. If it is a purely elastic case, then we say it is the strain energy. For purely elastic case, we call it as strain energy density. Otherwise, you can have Helmholtz energy or free energy depending on whether temperature is also changing or not.
Okay.
But for the purely
So
elastic case, it is the stored strain energy without the kinetic energy and the potential due to gravity. Okay?
yes, sir. So why I ask this question is because in the last lecture we defined for the hyperelastic material
Yeah.
like this. There exists a stored energy density function W, which is
Yes.
which you where you have mentioned below the stored energy is that strain free. So that's why my question was that for this case, if it is not strain, if it is not strain energy, then what kind of energy we have?
स्ट्रेन फ्री, मैंने इसलिए कहा था कि वो स्ट्रेन फ्री है, ऐसा तो नहीं लिखा था मैंने।
Okay, so
या मैंने लिखा था स्टोर एनर्जी या स्लैश फ्री एनर्जी डेंसिटी, ये लिखा था।
यस
ये
सर।
नहीं कहा फ्री नहीं था, या तो वो स्ट्रेन एनर्जी डेंसिटी होगा या फ्री एनर्जी डेंसिटी होगा या हेल्महोल्ट्ज एनर्जी डेंसिटी होगा, ये नहीं कि वो
ओके
स्ट्रेन फ्री एनर्जी।
ओके, तब मैं गलत समझ लिया था सर, इसलिए
सर
हाँ
स्ट्रेन एनर्जी था सर, फ्री नहीं था।
एनर्जी और स्लैश फ्री एनर्जी ये लिखा है सर।
हाँ ये लिखा था। हाँ
ओके ओके ओके, सॉरी सॉरी सर।
नहीं कोई बात
But
नहीं।
sir, how can it be that W, which is stored energy, how can it be that it will depend on different parameters that uh, जिसके मतलब on which basis will do the differentiation and then get P, sir. So the stored energy for a particular body or a system has to depend on a fixed set of parameters, right? So how is it be that can differ?
ठीक है, फॉर एग्जाम्पल सपोज टेम्परेचर भी चेंज हो रहा है, तो उस केस में जो स्टोर्ड एनर्जी होता है that is not just due to strain in the body but also due to change in temperature, तो वो दोनों को एक साथ बोलते हैं स्टोर्ड एनर्जी। तो वहां पर स्ट्रेन एनर्जी भी है और टेम्परेचर वाला एनर्जी भी है। और अगर इसको तुम मॉलिक्यूलर स्केल में सोचो तो एक है एनर्जी ड्यू टू मैक्रोस्कोपिक चेंज इन द बॉडी और दूसरा है एनर्जी ड्यू टू थर्मल फ्लक्चुएशन, एंड दैट्स नॉट द मैक्रोस्कोपिक काइनेटिक एनर्जी। वो थर्मल फ्लक्चुएशन जो है वो वो बॉडी को एज ए होल मूव नहीं करता है, बॉडी एक ही जगह रहेगा और फिर भी फ्लक्चुएट कर सकता है, तो उसके कारण टेम्परेचर चेंज होता है। तो इसको हम लोग बॉडी के मैक्रोस्कोपिक काइनेटिक एनर्जी में नहीं डालते हैं, तो इसको बॉडी के स्टोर्ड एनर्जी में डालते हैं, उस वाले थर्मल फ्लक्चुएशन को। तो तुम देख सकते हो कि कारण एक और मैकेनिज्म आ गया एनर्जी स्टोरेज का, तो उसको इसलिए उसका चेंज हो गया।
So in this case then एनर्जी को हम लोग डिफॉर्मेशन के रिस्पेक्ट में डिफरेंशिएट कर सकते हैं, टेम्परेचर के रिस्पेक्ट में भी डिफरेंशिएट कर सकते हैं, दोनों हम लोग पियोला दे रहा है डिफरेंट
दोनों के रिस्पेक्ट में कर सकते हैं, लेकिन पियोला जो है एफ के रिस्पेक्ट में ही करने से मिलता है। जो पियोला किरचॉफ होता है वो तभी भी डेल डब्ल्यू बाय डेल एफ ही रहता है, और उसकी प्रूफ है वो, ये सेकेंड लॉ ऑफ थर्मोडायनेमिक्स से इसको प्रूफ करके दिखाते हैं कि कैसे स्टोर्ड एनर्जी के डेरिवेटिव से पियोला किरचॉफ ही मिलता है, उसका प्रूफ है।
ओके
हाँ
Hello, sir. Like we have learned that in beginning, like del displacement gradient was equal to F minus I. So here, like, will we be able to apply that for this QF?
of course. So this is the reference configuration, then here is intermediate, and then you have further rigid body motion. Okay, Niranjana, is that okay to you?
Yes, sir.
So this is, let us say this 1, and let us say this is F2, and this whole thing is little f. Okay.
Yes, sir.
So now we know that little f is equal to F2, F1, and capital F is equal to, I guess, F1 into F2. Is it F1 into F2 F1? Yes, sorry, yes, F2 F1. Yes. F2 into F1. Also, you see, for the final case, F is equal to big X plus U, whereas for F1 it is big X plus U1, and for F2, well, F2 you can't say it is big X plus U2 because F2 is from intermediate to final. So anyway, so now this means grad F, sorry, big F is equal to identity plus gradient of U, and this means big F1 is equal to identity plus gradient of u1. Okay, and this thing is also equal to big Q into big F1 for this particular case. So you can see that this I plus grad U thing is always there. Just that you have different U. Whatever is the total deformation, the U is corresponding to that.
Sir, here you used omega is equal to the q dot q transpose. So
Yes.
there in like beginning we had taken del u and broken down into symmetric strain tensor, then anti-symmetric part rotation tensor, and then we had taken like the axial vector or dual vector for that anti-symmetric part.
Yeah, that was
We
okay.
got the
Yeah.
angular
So
velocity.
that was all for that was for linear elasticity. You can always, although you can always say that F is equal to I plus grad U, which is equal to I plus grad U minus grad U transpose by 2 plus grad U plus transpose by 2. So this you can always say, but saying that this is corresponding to rotation, so you can say that this corresponds to rotation only when grad U is much smaller than 1. So only you are working in linear elasticity regime that this part can be compared with rotation. If your grad U
Okay,
is
so
not,
the
yes,
so the angular velocity that we calculate there and define here, they do not have any relation.
yes, exactly.
Okay. Okay, so they do not have any relation. Here we define a new term like angular velocity, which is axial vector of the rotation tensor derivative into its transpose. So that's entirely different from the one
Exactly.
that we used at the beginning.
Yes.
Okay, sir.
Exactly. They are
I
entirely
already had that.
different. Okay.
Okay. Yes.
Okay.
Sir, we derive the angular momentum balance using the
Yes.
last method from the uh, and there we assume that the omega is constant, means body is rotating with angular
Yes.
constant angular
Correct.
velocity. And sir,
Correct.
and also we derived this angular momentum balance at time t equal to 0. So suppose we want to
Yes.
calculate angular momentum at any time t, can we define that, or it will be same as initial?
See, first of all, we didn't derive angular momentum balance. We were just going through that proof. Let me show you what we did. So we started with this relation, then we took the derivative and we came here. So this is something which holds for all time. But this was not useful to us. We then said, why don't we look at it at t equal to 0? So at t equal to 0, we got something is useful to us. But this relationship is general. Okay?
Yes, sir. Yes, sir. Okay.
So if there is no question, we can stop the class for today.
Yes, sir. Thank you.